after our discussion of Gould and of how to get representative samples. You might say, yeah, sure, that's great. I now understand why it's important. But you still might be wondering, yes, but even given a representative sample, why does statistics work? And how do people figure it out? Well, to understand the relationship between a sample frequency and a population, let's perform the opposite inference. Let's imagine that we've got a jar of 200 marbles. Half of those marbles are red, the other half are non-red for simplicity's purposes. We can easily calculate the probability of a given sample of a particular size having a given percentage of red marbles. And that's just basic probability theory of the sort that we learned during the probability theory lectures. Now you might think to yourself, you've lost your marbles, Wallace. But in fact, we can do this. So for instance, to figure out the odds of a sample with 4 draws from our jar of marbles with replacement, so that we draw a marble, we record its color, we put it back in, we shake it up, and then we draw another marble. We simply lay out all the possible outcomes. And that might seem kind of daunting even for 4 draws, but it is an easy way to do it that we learned in the propositional logic lectures. We can lay out all the possible combinations of color values for red and non-red in the same way we did our truth table guide columns. We have 4 draws. Each draw has 2 possible values, red or non-red. And that means that 2 to the 4th, or 16, is the number of total possible combinations of red and non-red that we could draw out, unique combinations. So we can start as we did in our guide columns by alternating off red, non-red, red, non-red, red, non-red, doing 16 rows. Then we go to the next column and we double that pattern, red, red, non-red, non-red, doing 16 rows. Then we go to the next column, double that pattern again, red, 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 non-red, 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 non-red. 16 rows. And the final row, the top half is red, the bottom half is non-red. And in this way, we systematically lay out every possible combination of red and non-red for those 4 different draws that we could possibly have. To determine the probability of each possible sample, we simply add, that is, we use the restricted disjunction principle, the probabilities of each potential way to get that possible sample. So there may be a number of different ways. We could get it this way, or that way, or this way, or that way. Since there's only one outcome, we know that they're exclusive, and so we can use our restricted disjunction principle and add the probabilities for each of the possible outcomes. The probability of each of those potential outcomes is just the product of each draw on the sample being the color that we want it to be. In other words, the restricted conjunction rule, because my draw 1 is going to be independent of my draw 2, and so on, because I'm replacing. So let's think about a case where we want to determine the probability of drawing a sample. 4 balls, or 4 marbles, that are all red, 4 reds. Well, we've got all our possible combinations. We look at all those possible combinations and identify every one that gives us all reds. And there's only one. I've highlighted it here in red. What's the probability of getting that draw? Well, half the marbles are red, half are non-red. We can use the classical interpretation, assume that each marble is just as likely as every other, and that gives us 0.5 to get a red for the first draw, 0.5 for the second, 0.5 for the third, and 0.5 for the fourth. And since they are independent, we can use the simple conjunction rule and multiply them. That gives us a total of 0.0625. That's the probability of drawing a sample of 4 marbles with replacement where all the marbles are red. And notice that getting a sample of 4 draws where all the marbles are non-red will have that same probability. There's only one way to get it. What about some of the other possible combinations? Well, suppose that we want to determine the probability of getting a sample with 3 reds and 1 non-red. Again, we just go through our possibilities. We find all the combinations that are 3 red, 1 non-red. In this case, there are 4. We can add the probabilities of each of those combinations using our restricted disjunction rule, because there's only one combination, so we can't get more than 1 as our outcome. So they are exclusive. And we calculate the probability of each possible combination by multiplying the probability of getting the marble with the color that we want. And again, I've simplified the problem by getting a jar of marbles that's 50% red, or half red, and half non-red. So the probability of getting 3 reds and 1 non-red is just going to be 0.5 times 0.5 times 0.5 times 0.5. There are 4 different possibilities for doing that, and so I will get the probability of any one of them, 0.0625, times 4, or added 4 times, and that'll give me the probability 0.25 as the probability of drawing a sample of 4 with replacement, where 3 of them are red, 1 of them is non-red. If we now graph the different sample frequencies, as I've done here, what we see is that they form a symmetrical or normal distribution where the most probable sample is the one that has the same frequency as the population, 50-50. As we move away from that population frequency, the probability of drawing a sample with a different frequency starts to decrease in a symmetrical way around that sample frequency. And when we get finally out here, in this case, no reds, in this case, all reds, we're down to 0.0625 as our probability. So a couple of things to notice. One is the distribution of sample frequencies is a normal distribution, a bell-shaped curve around the frequency in the population. Notice that it's not particularly probable, but it's the most probable. And we can see, as we'll see in the next segment, that this pattern becomes more pronounced the larger our samples are.